so this podcast is going to deal with properties related to IMFs. So IMFs tell us how attracted molecules are to like molecules in their, if we have a compound of something. So properties related to IMFs. So our first one is going to be, let's just do boiling and freezing points. Alright, so when something boils or freezes, simply what happens is, if we're boiling water, we start with water, we turn it into steam, it's still water. So whether it's ice, liquid water, or steam, we have this molecule. Alright, we have water. So whenever we change states, we don't break any chemical bonds. We simply change how close the molecules are to each other. So if something has really, really strong attractions, such as water, which has hydrogen bonding, what's going to be true about its boiling or freezing points? That temperature is going to have to be really high because it's going to have to be a temperature that moves those molecules so much that they break apart from each other. Okay? Again, we don't break bonds when we boil or freeze something, but we break the attractions between them. So the stronger the IMFs, equals higher temps. Again, hopefully that kind of makes sense, that we have to break our molecules apart, so we have to have higher temperatures to do that, but the stronger the IMFs are. The next thing we're going to talk about is, let's do viscosity. And viscosity has to do with the resistance to flow. So sugar, well, honey, which is made up of a bunch of sugars, is really kind of, or honey or syrup, is kind of really gooey and kind of oozy, and it doesn't flow very well. It's kind of sticky with itself. So again, same idea. The stronger the IMFs, the higher the viscosity. And again, viscosity is resistance to flow. So something that is highly viscous is kind of just oozes, like, I don't know, lava or syrup or honey. So higher viscosity. And that kind of, again, just makes sense. If it's sticky with itself, it's not going to flow real easily. Next thing, let's do evaporation. Alright, so on this one, we might think of, if we have a beaker over here, we have some water in our beaker, and if we were to kind of, look at this through a magnifying glass and look at just the water layer right here, alright, what causes evaporation? Well, what causes evaporation is we have some gas molecules up here, and we have a bunch of water molecules down here. So water has a specific temperature, and temperature is the average kinetic energy. So some of those water molecules are moving very quickly, others moving slowly, but the temperature is the average speed of them. So right here we have what's known as surface tension, right where the surface, where the liquid meets the gas, okay? It's known as surface tension. So if the molecules are really sticky, kind of think it as a red rover line, and our water molecules are trying to get through this line. Well, if they're really sticky with themselves, who's going to get through? Only the fastest. How come the fastest? Because they're the ones who are moving the fastest. So who could get through the red rover line? It's either the fat kid that didn't have to run very hard because he was just bigger than everybody, or it was the really fast kid who could run so fast his momentum had the kids break their arms. So the fastest things break through, and that's who evaporates. Well, if our surface tension is really strong, is much of it going to evaporate? Not much, because not as many molecules are fast. If our surface tension is weak, the temperature doesn't have to be as high to get through the red rover line. So here, if we say stronger IMFs, those are going to equal lower evaporation rates. And again, we have to get through that red rover line. So the stronger the Red Rover players are, the fewer players are going to get through the Red Rover line. All right. The last thing I think we're going to talk about is vapor pressure. And vapor pressure takes us right back to gases, which is where we began the year. And vapor pressure is something kind of like this. Let's say we have a flask this time. We could have a beaker though. And we have a stopper in our beaker. So we have some kind of liquid in here, and it's going to evaporate. And eventually, we're going to have a number of gas molecules. And what happens is an equilibrium is set up so that gas molecules are condensing and water molecules are evaporating. And at a certain point, this is in equilibrium. So there's only so much vapor that the air can hold, all right, based on the surface tension and evaporation rates of our substance. So the stronger the IMFs, again this relates right back to evaporation. If we have really strong IMFs, many or few evaporating, but only very few are evaporating. So there's less gas up here, and then some of the gas is turning back into condensing back into liquid. So the stronger the IMFs, the lower the vapor pressure. And if we have weaker IMFs, we have all kinds of things that are evaporating. So we have lots of gas particles. So we have a bunch of gas up there hitting the sides of the container, and it raises the pressure. So 4 properties that are related to IMFs. Kind of just know, are they directly related, are they indirectly related? So we might just go through your boiling and freezing points, stronger, higher temps. So we might just call this direct relationship. Viscosity, stronger IMFs, higher viscosity, so they both get bigger. So we might call viscosity a direct relationship. Evaporation, stronger, lower evaporation rates. So we might call this indirect. And lastly, vapor pressure, stronger, lower vapor pressure. So this is indirect as well. So 2 are direct, 2 are indirect, but be prepared for questions like that on your test.